Hello, hello. Let's see. Is this good enough to hear? Hi, my name is Tom Burns, and it is my honor to welcome you all here tonight. I'm the curator of the Harvard Plate Stacks collection, and tonight we are collaborating with the Harvard Science Book Talk as well as the Harvard Bookstore in presenting what will no doubtably be a wonderful evening. I just wanted to take a few moments to say that tonight is kind of an amazing culmination of milestones. It's been kind of a wonderful last 2 years working with Anna about this book in particular, but just seeing this whole entire project come into fruition has been such a pleasure for me. I want to give two plugs. One, to make the bookstore people happy. If you have not picked up a copy, you can get a copy both up in the auditorium, out in the lobby where you might have checked in, and then we do have a reception that'll be following upstairs on the 4th floor in the library. That is where Anna will be to help and not help to sign any of the books. And then we welcome you all to that reception. And then if you are interested in staying informed about the different happenings related both to this book as well as all of the other things that we do with the Harvard Plate Stacks, I encourage you to sign up for our newsletter. I only send it out 4 times a year because it's too much work for me and I hate spam myself. But yes, let's get back to the introductions. So I would like to introduce tonight's co-speaker, Professor Alyssa Goodman. She is the professor of applied astronomy. Oh, yeah, and one of the people who actually was the genesis of kind of all of this project as well. So thank you so much for coming, and see you after.
Oh, so I do introduce Anna. Yeah. Oh, I don't need this. Yeah. Hi, can you hear me? Yes. Great. By the way, applied astronomy is spectroscopy, which is what a lot of the work we're talking about tonight did, but they didn't have a word for it when they made up that title in the 1800s. Anyway, never mind. Hi. I am also incredibly happy to be here tonight because I have been at Harvard since 1992 as a professor, and before that I was a graduate student. We won't discuss how long ago, but actually this room looked very different when I was a student. Anyway, I have learned incrementally stories about my predecessors at the Harvard College Observatory, the women who really made all of these discoveries that are featured in Anna's book. And so that is why I am especially happy to be here. And during the discussion, I hope somebody asks us how people's perception have changed over the last 20 or 30 years, which is my experience, of the people that you'll hear Anna talk about. And so my job today is certainly not to talk about that history, but instead to talk about things like this graph that you see on the screen. So I just said to Anna before we started, is this graph somewhere in your book? Because the thing that Henrietta Leavitt, who we're going to hear a lot about tonight from Anna, is most famous for is now called the Leavitt law, was also called the period luminosity relation. This is not really an astronomy talk, so I'm not going to explain this in great detail. Some of you probably already know what this is, but I'm going to say that what Anna is going to focus on is how this discovery and everything that went around it, how it was made and who the people were that made it and what impact it's had since really came to pass. And what I'm supposed to do is just give you a little bit of information about math and science that'll help contextualize what Anna's going to say. So I am nowhere near as good an artist as Anna, so this is a picture of me. And then this is me at half scale, and this is me quarter scale, 1/8, 1/16, 1/32. I don't know if you can still see that. It's a very big screen, so maybe you can see that little dot for 1/100th. Here's 1/200th. Why am I doing this? Okay, I'm doing it to show you some context about numbers, about how far things far away are to measure in terms of their distance. Okay, so Proxima Centauri, for those of you who don't know, is the next closest star to Earth other than the sun. And these numbers, 200, you already can't see what's going on. is 270,000 times farther than the sun, okay, is the closest star to the sun. And so in terms of angular size, is what you see on the screen here, it's basically a dot, okay? And all stars are dots. And this is why, until relatively recently in human history, people argued about the distance to the stars and thought maybe they were pasted on some sphere, at some fixed distance from Earth, okay? But what you'll hear about from Anna is how suddenly the universe went from being two-dimensional to three-dimensional, and that Anna von Mertens, yes, she's very responsible. Henrietta Leavitt was definitely a big part of that story. Okay, so my summary of all of how hard it is to measure distance in astronomy is to just say that it's ridiculously hard and give you numbers. And so here's another set of numbers in a second. Okay, but as I just said, Henrietta Leavitt's discovery made it possible to measure the distances not to stars, but also to galaxies, okay? So she started by measuring Cepheid variables, variable stars that she was interested in something called the Small Magellanic Cloud, again, for those of you who know something about astronomy. But importantly, that is 47,000 times farther away than the nearest star, Proxima Centauri, okay? So she found that there was a relationship, which is what that graph is, okay, between the brightness of a star, a Cepheid variable, not any star, but a particular kind of variable star, and how quickly it fluctuated, okay, what its period of these fluctuations were and its brightness or its luminosity, okay? And that's what's graphed here. And again, we won't go into that unless you want to know during the questions, but what you need to know is that the same way that if you take a light bulb that you know its brightness and then you walk far away, even intuitively you can guess how far away the thing is, and quantitatively you can measure how far away it is. So if you know the intrinsic brightness of something, which is what you can get using this graph, okay, if you measure its period, you can then know its brightness. And it's much easier to measure the fluctuation in brightness of something than to measure its distance any particular way, okay? So what Edwin Hubble, who you probably have heard of, did was to use this relationship, which is now called the Leavitt law, to measure the distance not to the SMC, but to the Andromeda galaxy, which is a spiral galaxy like the Milky Way, and that is 13 times farther than the Small Magellanic Cloud. Don't worry, I'll put all these numbers together for you in a minute. Okay, but importantly, what that showed is that when you measure the distances to galaxies and their speed, their redshift that you turn into a speed, that the universe is expanding. Okay, and since what Hubble did, we've learned that this expansion is actually speeding up and that there's all kinds of unseen so-called dark matter, and we don't understand why the expansion is speeding up, and that's what gives you this concept of dark energy. So arguably this discovery that Anna will talk about tonight and put into context of really the attention, the focus of the book, the attention that Henrietta gave to these Cepheid variables and how this, as part of the whole story of the early Harvard College Observatory, came to be, is the story that you'll hear from Anna, okay? But just what you need to know is, yes, if you've been doing the math in your head, 270,000 times 447,000 times 13 means that, yes, Andromeda, the galaxy that Hubble started with, the closest one, is 165 billion times as far away as the sun. Okay, so when I say that it's ridiculously hard to measure distance in astronomy, it's ridiculously hard. Okay, so there's been a development that actually brought all of us together, all of us being the people in these pictures. Okay, so the two of these people you see in this room, that's me and Anna von Mertens, and the third person here is João Alves, whose essay you can actually read in Anna's wonderful book. And the reason I'm showing you this is, yes, we miss João, but how did this story start? Because Tom said that I was part of starting the story in a very tiny way. And the tiny way is that Jennifer Roberts, sorry, Jennifer showed me not to point her out, but here she is, art history professor Jennifer Roberts arranged for Anna von Mertens, who is a fantastic artist, graduate of Brown and with art degrees, and I would give a long introduction, but I don't want to take any more of her time. She's a genius, okay? But so she was invited to Radcliffe, where Jennifer and I were both directors, Jennifer of arts and me of science, to give a exhibition there that started this whole story, and Anna will talk about that. But importantly, at the exhibition, Anna met this other astronomer named João Alves, who was measuring distances, okay? Measuring distances using this thing called Gaia, which measures distances to stars, 1 billion stars in the galaxy with exquisite accuracy. Again, if you care, ask me at the reception. But importantly, Anna and João became very fast friends. And Anna and João talked about astronomy for a year. And during that year, we also were lucky enough to discover this thing called the Radcliffe wave, which relies completely on measuring incredibly accurate distances and shows the Milky Way to have a different structure than what we thought, at least locally. And again, you can read about that in Anna's book. But tonight is not at all about the Radcliffe wave. It's about Anna's wonderful book. And I just wanted to explain what it is that I'm doing here. And the answer is, I was there the day that João and Anna were introduced, and we got to do all these fun things since, and I've followed the progress of this, and I'm incredibly happy to turn this over to Anna, and thank you so much for coming.
Thanks, Alyssa, and thank you, Tom. Thanks for the support all along the way, and it's a theme tonight, but I have found that when you find something that you're interested in, well, you also find our friends that care about those things too. So thank you for your support and thank you for your friendship. And yeah, so as we think about this evolution of our understanding of the structure of our cosmos, the narrative of that usually begins with this image, the most famous glass plate in the history of astronomy. It was taken in 1923 at Mount Wilson Observatory by Edwin Hubble. He was tracking these new stars flaring into view in the Andromeda Nebula, it was called at the time. And he identified 3 new stars and marked them with the letter N. But when he went to compare them to the plate taken the night before, he noticed that one of those new stars changed in its brightness. It was not the characteristics of a nova, but of a Cepheid variable. So he crossed out that N, famously wrote VAR in red ink, but most significant to me is that he added an exclamation point, which is a unique notation to be found in scientific data. So I want to follow the path that leads to that exclamation point. I want to see why that exclamation point exists. And as we all know by now, that exclamation point exists entirely because of this woman, Henrietta Leavitt, who worked at the Harvard College Observatory for most of her years at the turn of the 20th century. And so I want to talk about that path that leads to that exclamation point, and also along the way, talk about the path that led to this book coming to existence as well. And I want to say right off the top that support from the MIT Press was invaluable to making this book a book, as well as the Sloan Foundation grant, which allowed me to tell the story as richly visually as I did in the written text, and with each page individually designed by the incredible John Kramer, who's here tonight. So we'll be talking more about John's design along the way. But my encounter with Henrietta Leavitt started with the glass plate collection. Jennifer Roberts invited me to develop a research-based exhibition here at Radcliffe, and because of our shared interest in astronomy, we toured the glass plate collection, which is the oldest and largest collection record of the night sky in the world. And on that very first day, I took this photograph, and we looked at plates that looked like this. And when studying those plates, I first heard Henrietta Leavitt's name. I learned that she made a discovery that gave a sense of depth to the stars, that helped us calculate and imagine our 3-dimensional universe. And because of the profundity of this story, as well as a real connection, it's interesting, Alyssa, that you begin with distances, because I sort of say out loud that my religion is the scale of the universe. I really think if you hold the scale of the universe in your mind, that the ripple effects from that holding is profound. So I wanted to tell her story. And that story begins with these glass plates that she studied. Just like Edwin Hubble, she studied glass plate photographs of the night sky, which were made by taking a pane of glass, coating it with a light-sensitive emulsion, placing it in a telescope, and starlight hitting that surface registered these black specks of emulsion as starlight. And like Edwin Hubble, she measured these circles of light to see where that information might take her. And this was a new technology, dry plate photography. And with advancements in this technology, it enabled these multiple hour exposures. So these faint stars could be pulled into view. And Edward Pickering, the director of the Harvard College Observatory for a span of over 40 years, was an early and eager adopter of this technology. Very much so. And really at this time, this quote from Sullivan Bailey really says there was no real foundation of knowledge that discoveries could be built from. And so Pickering really committed himself to the building of that foundation, knowing that discoveries would come from that. But with this huge influx of data, of course, he needed a labor force to process the plates. And he was both practical and progressive and decided to hire women to analyze the glass plates. And so they were hired as computers to reduce the plates, a word I like quite a bit. And this idea of that they are applying a mathematical formula to stars, translating into standard coordinates, but they're literally reducing the amount of information held on those glass plates to a somewhat manageable amount. Again, so that would be a future foundation of information that discoveries could make, or a current foundation of information that future discoveries could be made from. And this was literally called women's work, not only because the women were hired to do it, but also it was thought at the time quite explicitly that their woman's eye and hand trained in the skill of embroidery developed the skills that of this exactitude required for this kind of work. And this is the first John Kramer decided these beautiful full bleed chapter openers for each written text in the book. And so this is one of my favorite. And I'll just read one of the paragraphs from that essay just to characterize this shift in the field of astronomy at that time. So 19th century astronomy in the United States was dominated by wealthy gentlemen scientists, literally called gentlemen scientists, and focused on the positions and motions of celestial objects. Astrophotography held new promise. Advances in dry plate technology during the 1870s enabled longer exposures, and this accumulation of starlight revealed previously invisible stars. The 7 stars of the Pleiades constellation, for example, were transformed by a 3-hour exposure into a cluster of more than 1,400 stars. With this new depth of field, interest in the size and structure of the universe deepened. No longer dependent on the subjective impression of individual observations, astrophotography could make a record of this expanded space for deliberate, repeated study. The photographic plate became a site of shared knowledge. And so that summarizes this sort of real transformation, this shift in how discoveries are made. And the literal site of that shared knowledge is this building, the so-called brick building that was a fireproof housing for the glass plate collection. But also significantly, in Leavitt's time, only women worked in this building. So that very much calls to mind Virginia Woolf's A Room of One's Own. Well, these women had a building of their own. And it's interesting in this photograph, you'll see the observatory dome in the background, right? So it was thought that for a woman's disposition was too fragile to stay up all night in the cold and take photographs. So the men made the photographs, but the women in daylight were the ones that studied them. And there was a sort of subversive quality to this, that they sort of came in the side door and had this first point of access to this valuable data. And Pickering, being progressive, also gave quite a bit of liberty to the direction of the research for each woman. So yes, they were hired with one job description, that of a computer. They were paid much lower rate than men, and there was no possibility of advancement. But within that restriction, there's quite a bit of expansiveness that they could follow their own lines of research. And so here on the right, Henrietta Leavitt, on the left, Annie Jump Cannon. I don't have time to go into Annie Jump Cannon's work besides just providing the foundation of our understanding of stellar evolution. But other than that, so she has her own line of research analyzing these stellar spectra. And this gorgeous photograph by Jennifer Roberts starts to give you a window into what her Annie Jump Cannon's world looked like. And I'll talk about Jennifer's photography a little bit later, but basically anytime I show you an astonishing photograph tonight, Jennifer took it. So, and so Jennifer, being that ever since my invitation to the Radcliffe, we've sort of been side by side in this investigation. So on many, many trips back to the plate stacks, I know my little plate stacks posse over here. On my many trips there, Jennifer would accompany me with her phone and simply attach to that a macro lens. So pulling forward the richness of this world that these minds inhabited. And I'll talk again about the transformative quality of her photography, but I knew in making this book that I wanted the viewer to really exist with these objects versus looking at them. So that was one line of research. For Leavitt, it was magnitude work, really assessing the brightness of stars. And I love there's sort of a sincerity to this. We're in mind that there is no sense of depth to the stars. There's no way, as Alyssa said, to know where these dots of light were in space. So if a star shone brighter in the sky, well, was it intrinsically brighter or simply closer to us? There was no way to tell. And with this lack of information, there's such a sort of quality of faith in what information is present? Well, the size of this circle on this glass plate is the information we have. So we'll measure it and we'll see where that leads us. And where it led Leavitt was to notice that some of these tiny specks of light wavered in their brightness. They changed across plates over time. And she started to focus on the study of variable stars, these stars that change in their brightness over time. And when Leavitt began her research, there were maybe a couple hundred variable stars known at the time. So this is a very new field of research that she quickly became an expert in. And she first looked for variables in the Orion Nebula, this gorgeous glass plate taken, what date is this? 1893. So and she noticed in these nebulous regions where the stars were densely packed in these cloudy sort of literally clouds on the glass plates that they were rich in variables. She began her search there, but when Harvard established an observatory in Arequipa, Peru, to be able to capture the stars in the southern hemisphere and place there the most powerful telescope in the world at the time, these two celestial sites, these cloudy regions, these fuzzy regions of the Small Magellanic Cloud and the Large Magellanic Cloud, not yet even thought to be separate galaxies from our own, or satellite galaxies separate from ours. These fuzzy regions became her area of focus. And so these beautiful cyanotypes are from a photo album in the Harvard University archives. And I love that there's this, also that one of these pages is the nicknames for the mule that carries the plates from the observatory to the town of Arequipa. So I love that this photo album is simultaneously demonstrating the very leading edge of science, and it has such a familial quality to it, that there was this collaborative effort behind this forming of an understanding. And so Leavitt, this is one of Leavitt's astronomical logbooks. And so the Small Magellanic Cloud became an area of particular focus. And one of the techniques that Leavitt developed to identify variables is that she would take a positive of a region of the sky, here the Small Magellanic Cloud, and then she would superpose that over a negative taken of the same region of the sky. I like to show a broken plate every once in a while just to remind you this is glass. But she would superpose it over a negative taken of the same region of the sky but on a different evening. And only barely, it wouldn't sort of click into place. Maybe only a small region of the plate might align, but in that superposing, the dark circles, right, would cancel out those bright stars. But a variable might announce itself as a tiny misalignment of light. So that just might be a first indication that one might be a variable star. And then she would go and try to confirm her suspicions on a plate such as this. So here she's circled a suspected variable star at the very center. She has a standardized letter sequence. I mean, I'm just sort of throwing this at you of just sort of how complex her methodologies are. So here she has a standardized lettered sequence of known magnitude or fairly certain magnitude that ascend the magnitude scale, which of course is exponential. So every integer is 2.5 times brighter. So she toggles her eye between that suspected variable and along her magnitude scale, tries to find a match, and then goes to the next plate and tries to do the same. So she's trying to find these subtleties of shift and confirm this as a variable star. And here's another great photograph from Jennifer that even the subtleties, even the idea of a star being too faint, that was like the least of her problems. So I'm just going to go through a litany of what she had to deal with. That, again, this is a nascent technology, right? A very unreliable form. So this is a graph she's made to try to, the difference between the star registers differently from the center of the plate to its edges. And she's tracking across different telescopes the effect that has, the effect of different distance from center. There's also the challenge that light doesn't react in a linear way to the emulsion, so that by the time you have a long exposure to pull faint stars into view, the bright stars have gone off the rails. So you can't directly assess a bright star against a mid-range star or even a faint star on the same plate. So she would need to tie together or speak across plates, across telescopes, across different lengths exposure times. And somewhat famously, these objects are called fly spankers. And apparently Leavitt coined that term. So these are used to calibrate across plates. They're in the shape of a fly swatter, but of course are too small to do a fly much damage, apparently Leavitt said. So they're called fly swatters, or fly spankers. And here is a magnification. Even, I mean, it's almost like this gorgeous, the glue that sort of, if you find your way through that crystallized glue, you can see these little dots of light. So what they would do with these fly spankers is correspond the dot size to a magnitude. And you can see right all the way to that 12th magnitude, you see that size of that circle. So they would calibrate across plates. So they would, again, see how a star registered on one plate and then calibrate it using a fly spanker, linking plates to plates. So just throwing that all at you, it's all the more phenomenal that she discovers and announces in 1908 her discovery of 1,777 variables in the Magellanic Clouds. And she goes on to discover 2,400 in her lifetime, which is half of all known variables at the time. So she is literally the resident expert in this field of study. And here she starts to hint at her great discovery that it is worthy of notice that the brighter variables have a longer period. And she decides to study this more intently and makes a simplifying assumption. She assumes that the Small Magellanic Cloud is a single celestial entity. So any stars she finds there are roughly equal distance from Earth, and therefore any stars that travel their light to us, they would be equally dimmed by that distance. So that means that a brighter star found in the Magellanic Cloud would register as truly brighter on her plate. So here, the relationship between the stars are true for the very first time. And with this assumption in hand, I'm using this historic photo of the posed, granted, photo of the Harvard computers to show her next task is she wants to establish light curves for variable stars. And so you can see, I just love, because I've stared at this photo forever, but I only at the very last minute noticed that the light curve for beta Aurigae, is that how okay, I nailed it. Okay, Beta Aurigae is on, tacked to this wallpapered, but you can see those little data points of light, right? So that they're finding these data points across time and then stringing them together to form a light curve. And if you look at Henrietta Leavitt's logbooks, here she is, she's following two variable stars, number 10 and number 13, and then in this little sketch, finds another one, a new variable, and she labels it 86. So she's tracking these three variables across plates. And if you notice, one of those plates was taken in 1904, and the second one was 1890 and 1896. So if you think of where she's pulling these data points from, it's not like she's hitting play and sort of watching that light waver going from dim to bright and back again. She's pulling these data points across plates, across time, and somehow, again, she is the computer. She is holding this information. It's not retrieved anywhere. She is somehow holding it and forming an understanding. So it takes her several years to firm up this finding, but she announces this light curves for 25 of her variable stars in the Small Magellanic Cloud, and yes, produces this gorgeous curve. And because of the smoothness of the curve, first called the period luminosity relation, it could be considered law, and in fact now is called the Leavitt law. And astronomers immediately knew the significance of this, or the potential of this finding. If they could go and calibrate, this is my illustration for parallax. I'm not going to go into what parallax is, but if they could use a bit of trigonometry to calculate the physical distance to the very nearest of these variable stars, they could then turn back to the Small Magellanic Cloud, calibrate this relationship, and know how bright a star should be. And if it wasn't that bright, they could calculate how much distance was causing that light to dim. Okay, this elegant visual is not in the book, but it is elegant math. And I did just want to show, I just love the exquisiteness of math, that this inverse square law calculates that amount of dimming. So if you have a standard candle, in this case a battery-operated tea light, if you know the brightness of that star, you can witness and know that it's out there, the same brightness, but appears dimmer, you can calculate the amount of distance causing that light to dim. So for example, a star twice as far away is a quarter times as bright. 3 times as far away is a ninth as bright, and it follows down that curve. So again, this is how Leavitt reached out into the stars. She established this true brightness for this handful of stars, and then just observing the length of time a variable star takes to pulse, astronomers could calculate how far away it was, causing that light, the distance to causing that light to dim. So Einar Hertzsprung was the first to attempt this calculation, and he calibrated Leavitt law and placed the Small Magellanic Cloud as 30,000 light years away. And rather comically, at the time, there was a typo when his findings were published, and it was published to be 3,000 light years away. And just like jaws dropped, like they could not believe this sense of scale. And little did they know it was actually 10 times that finding. So right away, the very first application of the Leavitt law opened up this expansive space. And then what really bothers me is that, so when finding scholarship about Leavitt, was saying, well, did she know the significance of her finding? It's literally sitting right there in the middle of her paper that is published under her name, is saying, she publishes this graph and says, it is be hoped also that the parallaxes of some variables of this type may be measured. So there she is right in the conversation, aware of the significance of this finding. And this finding chart that is in the Harvard University archives of the Small Magellanic Cloud, I'm going to use this to demonstrate this this thought of, well, where can we take this finding? So yes, it was applied to the Small Magellanic Cloud. Does it apply elsewhere? And more photography by Jennifer. That one, I love that there's this little region labeled Miss Leavitt's region on this this finding chart, but also, right, there's these 2 globular clusters. And these are these weird sort of relics of the early universe, these conglomerations of tens of thousands, hundreds of thousands of stars that formed in the early universe. And they also hold variable stars in them. And so Leavitt herself was wondering, well, I've established this beautiful pattern of the pattern of light of these variable stars in the Small Magellanic Cloud have this pattern of light. And she's noticed that these variables in the so-called cluster variables have that same pattern of light. Well, does her law apply there? And there's uncertainty about this, but it reasoned with their same pattern of light that it would hold true. And Harlow Shapley, who would become the director of Harvard College Observatory after Pickering, he was based at this time as a young astronomer at Mount Wilson alongside Edwin Hubble. And these globular clusters were also of enormous interest to him. And he decided, and in this demonstration that Leavitt is a part of this conversation, here's Shapley's 2 excerpts of letters that he's writing to Pickering saying, hey, what else does Leavitt know about these? Does she think these like variable stars that blink at this faster rate, does she think this applies? Has she studied these stars in the Magellanic Cloud? So he's trying to shore up his research, which is in direct conversation with Leavitt's. And so he decides to go ahead and apply. And here in Leavitt's paper, again, people are saying, well, did she know? There again in her paper, she's asking, well, the limits to the massive variable stars of the cluster type. What are their spectra? So she's in this investigation as well. But Shapley decides to go ahead and use these strange relics of the early universe and apply Leavitt law to them. And it gets a little more complicated after that, but I will simplify in that he uses 119 globular clusters that he can find in the sky, and he maps them out, because at this time, right, we're just swimming in a sea of stars, and it appears as if there is no structure to them, right? We don't know at this time that most of the stars are hidden in galactic dust. It just appears this uniform dispersion of stars. But these globular clusters, only 119 of them, once he maps those distances to them, this strange shape takes form, that there is this clump of globular clusters, and we are far outside of that center. So here's already this sense of the shape and size of the Milky Way based on distances using the Leavitt law to globular clusters, and the sun far outside the center. So this is already astonishing enough, this new scale of the universe. And so Shapley is very famous for losing the great debate about whether these so-called spiral nebula or island universe are in fact part of this structure that he's mapped out, or are they separate from our own? And he sort of in the great debate says, I don't care, the Milky Way is so enormous, it must encompass anything and everything. And so that is why this plate is so famous, is that when Edwin Hubble finds one of those Cepheid variables in the Andromeda Nebula, he knows that he can prove it's so far away that it's outside of any scope that Shapley's established. So there's that ripple effect right away. And in it, I love finding this in the archives, that there's this light curve, right? So Hubble had to establish a light curve to prove its distance away. And he writes to Shapley, who by now is director of the Harvard College Observatory, and he says it shows the Cepheid characteristics in an unmistakable fashion. And what I want to point out here, right, so it's the most famous glass plate in the history of astronomy. It has one star identified, but he's recognizing something that has already been found. And so partly why I just walked you through all the subtleties that Leavitt needed to incorporate and fold in and be with is that she, through complexity, found something and knew how to find it. Whereas Hubble a little bit was like, yeah, that looks like one of those. So I like to just take him off the mountaintop for that little moment. And then he goes on. So with each Cepheid that's identified in a spiral nebula, it turns into a galaxy. There's galaxies all around us. And then showing their redshift of light, it's showing that the farther a galaxy away is from us, the faster it's receding. So in this span of a decade, we go from no sense of the sea of stars to this structure of the Milky Way, to galaxies outside our own, and to the universe expanding. And so that rapid worldview that shifts. Oh, I'd like to push Edwin Hubble just a little bit further off the mountaintop, because I like to point out that, so this is, of course, Einstein with Georges Lemaitre, and Georges Lemaitre was a brilliant mathematician, Catholic priest, who solved Einstein's field equations for an expanding universe, and he published that paper in 1927. Keep in mind, Edwin Hubble's famous paper is 1929. And he actually visited Edwin Hubble at Mount Wilson Observatory. And so his paper actually is the long title of his paper, Accounting for the Radial Velocity of Extragalactic Nebulae. So he's aware of Hubble's observations, has the math, and is the first to put those two together. So and again, because Edwin Hubble is probably one of the most famous astronomers, I do like to sort of push him off the edge, but more really is to talk about how a scientific discovery is made, how collaborative, how there are pieces that form and build a collective understanding. So this is my exhibition back in 2018 at the Radcliffe. And so again, walking us through that transformation of the Leavitt law being sort of offered out into the world and its implementation, creating this radical shift within a span of a decade, I wanted to make a monument to that life and work. And so I did what I do, and I made a quilt. I made a diptych, and the panel on the left show the stars above Leavitt's place of birth on the day of her birth, and the panel on the right shows the stars above the place of her death on the evening of her death. And I made my own sort of magnitude system for this using star calculation software. I assigned a numerical system for the brightness of stars. And then I played time forward again and again and again, tracing their light, assigned my magnitude a thread color in the grayscale, and then proceeded to stitch these paths of light. And so the length of each trail is according to how bright it is. So I would go through the grayscale to bring the stars back into view on the evening of her death, and those stars fade out from view on the morning of her birth. And of course, in that bracket of light is the span of Leavitt's life. And there is a risk at the time when I first showed this work at the Radcliffe, it was not only a testament to her life and work, but it also felt as almost a eulogy, because her very presence, the evidence of the presence of her life, was at risk of being erased. Because on back at that first day in the plate stacks, when I saw plates like this, I saw this plate, but I also saw this plate. And this plate's jacket reads, this plate may have been used by Henrietta Leavitt for her 1908 paper on the variables in the small Magellanic Clouds. And note, there were no markings on this plate as of 2016. They'd been cleaned off when mended for dash. And so this is part of the digitization project when this valuable resource, this only record of the night sky spanning 100 years back, wanted to be digitized so it could be opened up to time domain astronomy, this ability to study objects over time. It was deemed necessary to get clean astronomical data that a cursory JPEG, color corrected, would be taken of the markings, and that side would be wiped clean so that it could be rescanned at a higher resolution to get that astronomical data. And so literally the object that brought Leavitt's story to me, those objects were being erased. And so it felt like pure heartache. In some ways, making a monument to her life and work felt like a memorial. I felt sort of useless in this loss. And I talk about this entire project in this chapter, Data's Presence and Erasure. And what I am so thrilled about is that it felt like there was just this sort of cargo ship sort of headed in this one direction, and the sort of the volume of scanning of plates at this rapid pace just could not be turned around. And I am thrilled to say that that cargo ship came to a stop, has entirely turned 180 and is headed in the other direction. So there is a way now that it has been pledged that no glass plates will be erased. There's a way that these two sides of the glass, this is maybe my favorite photograph of Jennifer's, this floating letter B on her surface, Leavitt's side of the glass. It's an outlying from a standard sequence of hers on a plate. And it's trying to reach, right, the other side of the glass, the emulsion stars. And in the digitization project, both sides of the glass are being given equal weight, equal value, and they're being restitched back together. And so I tell part of that story, and part of the story I tell is the caretakers, the sort of that have been champions for Leavitt's story. One of those people very much being Lindsay Smith, and here her own notation, reject for dash, so that plates like this remain preserved, as well as Leavitt's presence. So with Leavitt's presence reasserted, what else is held in that life? Because there is another sort of heartbreak to this story, is that Leavitt's life was cut short by cancer, and she died in 1921. So that famous glass plate taken in 1923, she missed seeing by just 2 years. And so if I think about the life that builds towards something, right, it builds towards a discovery, and you miss the discovery, when I turn back to the path that leads there, I think, well, what did that path hold? And that path held such richness. So in these pages of her logbooks, the engagement and the dedication and the commitment to this investigation is so evident. And somebody in a talk I just gave pointed out this looks rather like an Emily Dickinson poem, and I couldn't agree more. And what also finds, as I said, when you find something that interests you, you also find friends that care about that work. And so this group of extraordinary women cared about the work, and in that caring for the work, cared for each other. A remarkable fact about this group of women is that almost exclusively none of these women chose to marry, and none of these women had children. For white women of middle class and upper class backgrounds, such as this group of women, the expectation is that when you were married, that you would leave your employment. And no doubt there are individual choices to each one of these women behind the decision of each one of these women. But there is no doubt an outlying choice. And I do believe that there was a way that they were committed to the work and committed to each other. Another extraordinary fact about these women is that both Annie Jump Cannon and Henrietta Leavitt were described in their lifetime as deaf. And that term is defined differently now from then, but the facts around that seem to be that Leavitt had a progressive loss of hearing that was resulted in a complete loss of hearing, and Annie Jump Cannon had a bout of scarlet fever at Wellesley that left her very hard of hearing, although she was known to attend the opera wearing a hearing aid. And I bring up that fact really almost just because it was not an accommodation that was made really in society, much less in the workplace. So the fact that Henrietta Leavitt's obituary, written by one of her colleagues, does not mention the fact that she was deaf is a sort of a recognition that it's come as you are, who are you, and you folded into this family. And I also like this photo, in contrast with this photo, that there is a warmth and intimacy to this relationship, but then you also see these two towering figures of modern cosmology. And Alyssa alluded to this, but I think for me, one of the surprises, again, one of the assumptions I had that sort of attention to this story sort of made me see things more clearly, is that these women were not sort of on the sideline. They were not sort of seen as assistants, sort of supporting future work. They were at the very heart of investigative research. And this sweet letter by Leavitt's mother, written to Shapley a week after she died, says this wonderful sentence, but while she was so modest about it, a remark once in a while showed me that she understood the standing she had among the astronomers. And this photo demonstrates that quite nicely, that there's a 1910 gathering of the American Astronomical Society. European delegates are part of this as well. And right, again, the women are not sort of off to the side or seated, or they are integrated and fully a part of this. So those letters of Shapley inquiring about Leavitt's research, that way that Leavitt is responding in her scientific papers to where the field needs to lead, all of that is very present and evident that these women are at the very heart of the boundary of our understanding. Another question I asked was, well, how do these women identify themselves? And I like declaratively that Wilhelmina Fleming seems to know the answer. So this is her gravestone in Mount Auburn Cemetery. And this gravestone, this gorgeous one-word astronomer emblazoned across her gravestone, was brought to my attention by Maria McEachern, a Harvard librarian here tonight. And that's part of the story I tell in the book as well, that there's this web of connections that David Sobel, whose beautiful Glass Universe book established this context that a brilliant mind and a story about Leavitt could rise from. And David said, oh, if you're about to conduct research, you need to know Maria. And oh, by the way, every year she sends me a photo of Wilhelmina's grave. This is a colleague of Leavitt's, and she places flowers there. And now I too get these photographs from Maria, and they are part of this piece of text in the book that is about how these women are identified and how they identify themselves. And in case there's any last need for crystal clarity, here's a 1920 census, just the year before Leavitt died. And here in cursive is that rare, beautiful word, astronomer, among words such as nun, teacher, maid, clerk, astronomer. And so the last thing I'll touch on before we open up to conversation is just sort of this, the irrelevance of Leavitt's finding that continues into contemporary cosmology. So for this chapter, I interviewed Wendy Freedman, who led the Hubble Space Telescope Key Project. And this is just a fun sort of commemorative, the Hubble Space Telescope documented that variable that Hubble found in the Andromeda Nebula. But Wendy, so the key scientific mission of the Key Project was to measure the expansion rate of the universe, right? So if you have this relationship between distances to galaxies and radial velocity, the slope of that line is called the Hubble constant, which I'm also like yet another thing named after Hubble. But the slope of that line is the expansion rate. And so by refining measurement to those galaxies, right, if the galaxies are refined to be farther out, that slope lowers. If the galaxy distance come in, that slope raises. So the expansion rate of the universe, and therefore the age and size of our known universe, are dependent on, of course, Cepheids. So here's the 800 Cepheids Wendy and her team sampled, and look at that, just the elegance of that fit against the Leavitt law. So there's that principle that she established so long ago, helping us know the age and size of our universe. And even Wendy's time on the JWST still remains with Cepheids. It's helping. I won't even get into yet another thing named after Hubble, the Hubble tension, this question of what is that expansion rate, and she's using Cepheids to tell us. And when Wendy shared with this image with me over a conference call, it took me a moment to realize, like, oh my, Wendy's measuring circles of light. That's what she's doing. She's doing it with a very different tool at a very different place beyond our moon. But nonetheless, she is measuring circles of light and seeing what that information can tell us. So I'll end with this plate in this drawing series I made based on this plate. This plate was taken in 1934, and it shows this wider field of view, so the Small and Large Magellanic Cloud and this bright star Achernar. And taken in this time, 1934, we can calculate, because of the Leavitt law, the distance to those three primary objects in space. But of course, in Leavitt's lifetime, it was just a two-dimensional surface, a sheet of glass. And so I made this drawing based on that glass plate, just to sort of apply my own attention, trying to follow Leavitt's path. So first I made a graphite drawing of the plate itself, but a particular quality of this plate, of this distortion at its edges, captured my attention. And because of the wide field of view, that the artifacts produced by this warping of the starlight produced these really strange, sort of almost like mythical creatures at the edges of the plate. So I made another beautiful photograph by Jennifer. I made drawings of magnifications of these plates, just sort of following star by star by star. And so here, from a distance, is what these drawings look like, these magnified sections of the plate. But this is exactly why I didn't want this to be the representation of my artwork in the book. Again, I didn't want my artwork to be something you looked at, but to be something you exist with. So Jennifer, again, took her macro lens to the surface of these drawings and sort of cataloged this taxonomy of shapes, these strange warped stars. And they operate in the book in quite a delightful way, I think, because right, you don't quite understand what you're looking at. They take it back into the realm of abstraction. And you're right on that edge of, I'm interested in these things. I don't quite know what I'm looking at, but if I pay attention, it might lead me somewhere. And so some of these drawings populate the book. Here you can even see the pressure, the little moon craters I create with that pressure of the pencil, star by star by star. And seeing this star and following the sort of working and studying these transmuted shapes reminds me of Leavitt's process, right? That she didn't know what she was looking for, but she knew how to find it, one measure of star at a time. And attention will lead you to surprising places. It's sort of a matter of faith of just staying in that attentive process. I certainly didn't think I was going to be making a book at the beginning of this path, but it's sort of paying attention brings you to a place of discovery. But then also in examining Leavitt's life, there is also, of course, attention as its own destination, that richness that is present, and the friends you find there. So thank you. Okay, yeah.
I mentioned she was a genius, right?
No.
So she also, I just want you to appreciate that she said a graphite drawing. The drawings that Anna was showing you there and the photos at the end are almost indistinguishable from the actual plates. And the amount of attention and care that she needed to apply to that is just astonishing in the modern world. And so I just wanted to ask you a question, which is not an easy question. So we might need to have the audience add on to this question. And the question is, in the modern world, okay, we don't have artifacts like this. Mm-hmm. So in other words, a lot of what we do today in astronomy is data science, okay? Which Jennifer, in her essay in the book, uses this wonderful word, pre-covery, where you have this huge amount of data and you don't quite know what you're going to do with it, but you have some intention, and then later you make amazing discoveries. And that's what was happening 100 years ago, and that's what's happening now. Okay, but the difference is that we don't have beautiful annotations and personalized anything. And so my question to you is, if you were doing this project 100 years from now, what do you think the connections between, the attention that hopefully an artist is still going to be paying to what they do? Let's not talk about Dali, okay? But and what we're doing now.
Well, it's interesting that you say that you don't have artifacts now, because we've been hanging out with Ido Berger and studying gravitational waves, and he revealed this image to us that, he's like, oh, here's the chirp that proves, and he's like, and he showed us this image that had this big artifact in it, and it was, I'm making it up, but it was almost, Jennifer, do you remember what it was? But it was like a truck rolling by, let's just say it was, okay? And Jennifer and I were both like, wait, that is
so... Sorry. Yes, true, but I didn't mean artifacts like...
oh, you didn't mean literal artifacts?
I meant artifacts the way computer scientists use art. I meant like notations and extra stuff.
Oh, I see. I got you right. Okay, that is, okay. Okay, because I do want to,
there are plenty of artifacts.
Okay, I was like,
no.
I was like, there are plenty of artifacts, I know, and I wanted to stay in the land of artifacts. Yeah. But that is true, right? That material richness that is lost, and that is a little scary. That's scary for all of us, right? There is that way of like, if you take childhood photos and they actually exist until, right? So we think we all have a relationship with the material, but it's all the more advocacy for material, right? So that bringing it back into the material, and the way that I made those drawings sort of was a way to more experience Leavitt's skill and attention. So I guess my answer to that simply is, do not abandon the material, because that is where a different kind of intelligence lives. And so I think there is a way that we hold on to that.
And then the other point I wanted to elaborate on that you just heard Anna talk about, that I think would be another good conversation among all of us, is about this issue of erasing the annotations on the plates. And so what actually happened, to be completely clear, is that this project was started in a very ad hoc way a long time ago by one of our faculty members who is not himself any kind of historian or artist, and it was a very valiant effort. And what they did was take photographs, which were high resolution at the time, but not very high resolution, of the plates before they were erased. Okay, so it's not that they were erased and eradicated forever, they're just not preserved as the, again, computer science will say artifacts, we'll say articles or things, okay, that they were. And so that is definitely bad from a historical perspective, but it's kind of understandable as to why it happened. And so I'm curious, because now, yes, it's not the Hubble tension, which, by the way, it's all the same thing. The Hubble law, the Hubble tension. I know. It's just the same guy. Anyway, but it's a tension between the people who are seeing the Harvard plate collection of nearly 600,000 glass plate images of the sky as a giant archive of objects to be preserved, and the people who are seeing this as an unbelievable treasure trove of data. Because just to emphasize the data part of it, there is no way to get 100-year time baseline of the observation of anything except to wait 100 years, okay, or to go backwards in time 100 years. And so it really is a treasure trove, even though we could do much better now in terms of sensitivity and fewer artifacts, okay, but we'd have to wait 100 years, okay, to go from where we are now to 100 years at any other point in time. And so there is an argument to be made that it's a tremendous data resource. And so there's, a debate to be had. And personally, I feel that both should be done and both are correct, but there may be people in this room who disagree with that. And then the last thing that I hope that we can talk about a little bit is this kind of revisionist history. So Anna also just mentioned something that happened to me, which is, like I said, my first experience at the observatory was in 1984 when I was a graduate student in the physics department here, and I didn't know anything about. I was not even an astronomer, and so I started to hear stories about Cecilia Payne-Gaposchkin and Henrietta Leavitt and Wilhelmina Fleming, and there are some sort of famous people among these Harvard computers, not including Cecilia Payne-Gaposchkin, who was later. But anyway, and you hear these stories that make it sound kind of cute. Okay, like, oh, there were these women and they were kind of helping out. And it's like, that is completely wrong, okay? And when you talk to Deva, which we've both done, she thinks that part of it is that the 1950s kind of recast women in this kind of different maternal housewoman role, and that the history just kind of changed, and that by the time I would have come into this story in the late 1980s, that was kind of still sticking around. And so now all of this, like, let's rename it the Leavitt Law and let's see what these people have done. I'm curious, how much this has kind of penetrated the consciousness. And I think the undergraduates, so Anna came and spoke to some undergraduates a couple weeks ago, and I think they didn't know the story. And I think that the way that the story of women in science gets told these days, it's like everybody was always oppressed, and now we're trying to liberate everyone. And it's like, that's not true, okay?
Yeah, and it's such an interesting thing, right? Because, the women did not have the right to vote, and it was literally, you come across documents that say a woman's college education might make her infertile. Like, those are real things that they are dealing with. And at the same time, these women, as I tried to demonstrate, were so integral and part of the conversation and part of the investigation and at the leading edge of discovery. And
being suggested for a Nobel Prize. You want to tell that story?
And being, right, and unfortunately Leavitt died, but a few years after, that was put forward as a possibility. They don't give it after death. But yeah, so I think, again, for me, like, that's part of this idea of attention, like making this parallel with discovery. And I didn't get to the discovery of the Radcliffe wave. You'll have to read about that because it's way too complicated. But part of what you do in a scientific discovery is sort of, what is my preconception, what are my perspective that's shielding me from seeing what's there? And so that was partly doing this research and seeing these women as like, oh, no, it's our sexism that we're layering on top of this history, and sort of like washing that away and seeing this story clearly is really, yes, as foundation. Think of Cannon and Leavitt as the two founders of modern cosmology. So, yeah.
Anyway, I just wanted to sort of set the stage a little bit. And do you want to say anything else before we open it up to the
audience? Go. Yeah, if there's any questions.
Is that actually Josh?
Oh my goodness, it's Josh.
This is the person who started the DASH project valiantly. Josh, we can't hear you. We need
Let me
a
get you a mic.
So I started this whole project.
Still can't hear you. Is that on?
Yeah.
Oh, it is,
Speak
but
loudly. 2002, I thought the time had come to digitize the plates, the world's largest collection, and an absolutely invaluable collection. And so in any case, I won't give you the whole history. But we went through, or I went through, a lot of preparation for this, including surveying the historical division of the American Astronomical Society. Should we clean the backside of the plate to not be confused in our digitization by what were artificial lines? And at the same time that we would photograph the plates to the best of the technology of the time, which was 2002. We actually didn't start the scanning and actual processing of plates, excuse me, until about, it really was rolling in about 2006, 2007, when we had a processing pipeline which was producing believable magnitudes. We made all sorts of refinements to take out effects that Anna so beautifully showed of distortions on the plates due to vignetting of the plates. We had all sorts of things built in. But in retrospect, I agree it was a shame to have erased those plates. But we did it after the survey, once again, that we wanted to get the best digital data from what is going to be the only collection of its sort. As Alyssa said, we'll have to wait another 100 years to get the same timescale. Discoveries are now rampant. We have a large number of discoveries that haven't come out yet because we wanted to wait until we had completed the digitization, which was this past May. It's all done. 556,000 plates, 500,000 plates. And we waited until the crown jewel plates of the collection, the large A plates, gorgeous resolution. They're 14 by 17 inches, big pieces of glass. None of them were broken. The crew that did the handling of the plates, some 15 to even as many as 20 people that were working part-time. They did a beautiful job, and the software development was very ambitious and worked. It kept up with the improvements in astronomical position, going straight from the very first rather crude positions that were available for the digital sky survey, which allowed the Hubble telescope to fly, to the much more refined and accurate positions, and not only just positions on the sky. With 100 years of data, you've got to take into account proper motions of stars. Stars
Thanks,
do
Josh,
move.
can I ask you a question?
So all of this was, accomplished. And again, the discoveries are really exciting. Let me just mention one that probably most people here have not heard of. We discovered, when you have 100 years of data, that the very first quasar, the discovery of quasars in 1961, it's a 13th magnitude star, and it looks like a star, but it's not. It's a galaxy with a supermassive black hole in its center, and now we call these active galactic nuclei, or the most luminous ones we call quasars and blazars. We discovered something that had never been noticed in this very first quasar, that when you have 100 years of data and you measure its brightness, we discovered a 16-year period. And it's due to the wobble of the jet in the quasar. It's a
great
resolved
example.
jet on the plates.
And Josh, let me just ask you to clarify one number, and then we should thank you.
So
because
anyway,
this is great.
I just
Josh
want to
was
let
here.
you know that there
So
are
this
a
is the
whole
guy who started the
range of
project.
discoveries.
And Josh, is it right? I remember a number. I think you once told me that any particular position in the survey on the sky was observed an average of 400 times over those 100
Of that
years.
order, yes.
Is that right? Yeah, it's pretty
And the
impressive.
data are much more accessible now. All
Yeah,
of the
there's a
data are
beautiful new
now
website.
available. You can all
check it out.
log in
Okay.
to dash or into star glass.
Let's go way in the back. Thanks, Josh. We'll go way in the back, and then we have Bob Simcoe here, who built the scanner. Trying to go to some outsider first, then we'll come back to the insiders.
Hey, Anna. I'm blown away the entire time that I've known about this project of the depth of research that you've done in order to make these discoveries accessible for viewers of the exhibition, of readers of the book. But I assume that an equal amount of time as you spent researching and going through these archives was really committed to your unbelievably precise, time-consuming rendering of these plates. And I'm curious if there's anything that you learned about Leavitt's research that came from this really close observation and recreation that perhaps was, continued to baffle or elude you when you were actually doing the kind of scientific research, but became illuminated through that close attention.
Thanks for the question. Well, I learned so much from Leavitt. And again, I think this project trying to speak to multiple layers of intelligence. So one thing I learned even about, I do make very labor-intensive objects. And I do also, part of why I make those objects is I think, and that's why the plates I find are so important, is that objects are such an effective way to preserve a story and carry a story through time. So I put my labor in these objects hoping they can tell a story. But in encountering Leavitt's work, it was also just realizing that idea of a destination was true of my own thing. If that sort of, I suffer to make the object and then the object lives this beautiful life. It was like if the path itself of making that object wasn't its own destination, why make these things? So that is one of the gifts that Leavitt has made. I do and think specific to her methodologies, which I try to sort of convey, is like the level of subtlety. Because I think, again, there's this sort of dismissive of like, okay, so she figured out these wavering stars. Okay, that's not that hard to figure out. The brighter, the longer it takes to pulse. And so when I go into her methodology and think of what she had to navigate and assimilate and find, again, how do you find something when you don't know what you're looking for? And so really this faith in the process is what has struck me so deeply in Leavitt's work.
I'd just like to add to that, which is that this screen is gigantic. And I was sitting here in the front row, and I actually saw things in the images from Jennifer and from Anna's work that I had never seen before because I could look at them so closely and my eyes aren't that good. And so I think that there really is something about what you called close inspection that really does make a huge difference. And
that was one thing I learned too, because you always, it's talked about, she measured the circles of light. So a couple things. One, they're not circles ever.
Hugely
and also that I learned that she also learned to assess the density of the emulsion, the density of black, so that the subtleties, again, the level of trained eye that she had to have was astonishing.
Yeah, the distortions in the images in these plates are much larger than the variations if you don't account for them. And so there was a huge amount of science and technology and math in actually just getting the data to be useful enough to do what she did. So Tom, I think we have Bob.
Yep.
Thank you for the question.
And while we get the microphone down there, another methodology I learned is that like getting bright stars and dim stars to be in conversation with each other, they would put a prism at the end of the objective end of the telescope and offshoot, or it would sort of siphon off a percentage of the star's light, and she would call those offshoot stars that she would then measure against dim stars. I mean, just like the inventiveness of the photographic techniques was astonishing. But go ahead. Hi.
Well, from the very beginning of the DASH project, there was a question among the astronomy world as to whether or not the plates should be digitized because you might lose some data and digitization of them. So I was pretty much aware of that as we built both the scanner and the process for capturing the data on the jackets and the data on the plates. And probably a lot of people didn't realize it, but I selected a lens that allowed us to be able to match the front and the back of the plates accurately enough to know what stars were pointed to by those things. Now, you have to do some manipulation in order to reproduce a plate in a way that you can see it, but it can be overlaid. And at one point in the project, people decided to buy a new camera, and I wound up having to go back and say, put that other lens back on, because that's the only lens that's going to maintain that relationship. So we tried as best we could to not lose any data of any form in the digitization process, even though it may take some work to go back and reconstruct it if you want to do that. Mm-hmm. And a lot of the plates that had marks on them, right? We had no idea what the marks meant. So we assumed somebody might want to study them historically, so we tried to do that. So we did our best to preserve all the data that we could.
Yeah, that's what I was going to say. In other words, I think there's versions of this story where it sounds like, Josh and Bob and the people who started this project didn't care about the historical value, and that's not true. And so it's just that it was a long time ago. Josh, I think we have to let somebody else ask.
Yeah, and we'll need to get out of our seats eventually soon.
Yeah.
Plates that were worked on by Henrietta and all the other luminous, wonderful women, we set them aside based on the jackets and the logbooks, who took that plate, who was working on that plate. So we did our best to preserve those plates. So set aside some 400 or 500 plates, which were not clean tracks on both markings were not those.
Yeah. So, yeah. I have, I guess, a little bit of stuff that I can share. So starting in 2002, we stopped, the project was stopped related to some technical issues.
2020.
Oh, 22. Sorry. I'm so young. That allowed us to reevaluate, make some more, try some different things out. And so all of those plates that were left, which is around 20,000 plates, they're the largest plates in the collection. We actually ran them through the same systems. We just didn't clean the plates. So those annotations are preserved. But yes, my predecessor, Lindsay, went through 400,000 of the plates, and out of those she was able to preserve and set aside around 660. They're now called the Wilhelmina Fleming collection of plates that you can go onto our website and read all about them. And then I would like to just take this conversation upstairs, I think, and we will all be around. There's books to be bought in the back, and then also upstairs, and then there's drinks.
Can you specify upstairs?
Upstairs. So we're going to the 4th floor. It's the library. So you can take an elevator to 4 if you take the elevator by the red entry hall, or you can take stairs either way up. All right?
Thank you.
Thank you so much.
Thank you.